Okay, the next speaker is Gustavo Fur. He's presenting the paper Robust Patch-Based Pedestrian Tracking using Monocular Calibrated Cameras. He's joint work with his advisor, Claudio Young, at Hooks, and we have 20 minutes.
So, hello everyone. So I'm Gustavo Fur, and this is our work, as Xiaomi mentioned it. So today I'm going to talk a little bit about the problem. First, the introduction about the problem of pedestrian tracking. Then I'm going to show you the method that we are based on. Then the proposed method that we divide in 3 stages, the experiments that and the results that we have, and some further and current work. So first, the introduction. What is the goal here? So the goal here, it's obvious. It's to estimate the pedestrian 2D position at each frame. So here we have the trajectory of this pedestrian. This is what we want. And the context here is surveillance systems. So we are assuming a single camera and a camera that is calibrated, okay? So this is important to keep in mind. So there are 2 major aspects of our method. The first one, I said before, is that we assume a single calibrated camera. And the second one is that we divide the target into several no overlapping fragments, like we see in this picture here. This is to handle partial occlusions, okay? So we track each patch individually. I'm going to talk more about this later. So the related work, there are several. I'm not going to talk about all the methods that we have for pedestrian tracking, but the main thing is that the problem is still open, largely open, because we have several difficulties. We have occlusions. Sometimes we need real-time performance, like in our case, because it's surveillance systems. And we have appearance change, depth ambiguities, etc. So we are going to tackle 2 main challenges here. So it's occlusions and real-time performance. So our method is based on the method of DEAL. So the main idea of DEAL is that we track each patch in the left here individually. So we have a set of displacement vectors in the image, and we combine using weighted vector median filters, WVMF, to estimate only a single vector combining all these vectors here. And this is the displacement of the target. Then we displace all the patches using this single vector. We're going to do the same thing, but we are going to advance on that idea and add some more ideas. So the proposed method, the first thing we're going to do is initialization. But first, what we are trying to do here is that we assume that we have a camera calibrated. So as we have a camera calibration, let's try to use this at most of you can. So we are going to use the camera calibration in 4 ways. So the first thing is that the displacement vectors are going to be combined in the world, not in the image, like we saw with the method of DEAL. And another thing is that we are going to align the patches along a vertical line in the world, not in the image. So in the image, we're going to have something like this. It's not vertical in the image, the alignment of the patches, but it's vertical in the world. So the orientation of these patches is going to match pretty good the orientation that we see in the image. This is going to be clear in the visuals. So we also define a search region in the world, and we estimate scale using the camera calibration. So we use as much as we can. So the first thing is how we create these patches at the first frame. So I did a very beautiful animation here. So first the user selects the foot point, like mark here. Then we are going to draw a line that is vertical in the world, and we project that to the image. We have this line. To assist, the user selects the head point. So now we have the head point and the foot point. We have this line. We are going to create the patches there. So, as I said, the patches are aligned in the world, so according to this line. And another thing that we are going to do is to extract the height of each patch here using the projection matrix. This is going to be important in the tracking step. So now the tracking step, the first thing we're going to do is match each patch with several candidates and choose the best one. But first we need to create these candidates. So we are going to define a search region in the world, like I said in the beginning. The first thing we do here, this is the world. We have the ground plane here, which is z equals 0. And we extract the target ground point using the homography. Pretty simple. Then we have this point. We are going to define this search region in red using this equation. The size of this search region is this equation here. So it's the maximum interframe displacement of a person in the world. So we put here that the maximum velocity of a person walking would be 1.5 meters per second, and we use the frames per second also to compute this distance. And we have a relaxation parameter to recover from failure and stuff like this. So now we have this search region that is the same size at each frame in the world, but it's not going to be the same size because in the image, because we are going to project this in the image and sample these points here to create the candidates. So it becomes clear that the search region's size is going to depend on the position of the person, which is a good thing. If the person is too close to the camera, we need more candidates because the movement is going to be bigger, perceived by the camera. And when it's small, the movement is going to be smaller. So we have two examples here. You see that the search regions are not the same size. So now we have this set of candidates for each patch. We are going to match this. And we use two features here in the paper, but this is not our main contribution. You can add the feature that you enjoy, that you like, and you can use in this framework. But we use covariance matrices, which is also known as covariance tracking, and it's just the covariance matrix of the RGB pixels in the patch, and color histograms. And here we have lab images, and we use only the A and B channels because the L channel is sensitive to illuminations. Okay, so we're going to compare each candidate with the model that we have, that we compute in the first frame. And for the both case, we use Bhattacharya distance. And this is it. Now, what we have right now for each frame is a set of displacement vectors in the image. But I said to you that we are going to combine them in the world, because in the world they are more coherent. So we are going to assume that this place is parallel to the ground plane. So in the world, we are going to assume that this displacement is only translational and parallel to the plane. So we have this equation here. It's just the projection matrix here. And we have this hi, which is the height of the patch that we compute at initialization. So this is going to be we have two unknowns here, x and y. And we have two equations, so we're going to have a linear system, 2 by 2. So now, using this equation, we can reconstruct these vectors in 3D. Now, the idea of the WVMF, as I said before, is to combine these. We are going to combine now 3D displacement vectors. And the WVMF is going to associate a weight to each of these vectors. So this weight is this equation here, depends on two things. First thing is the distance from the vector to all others. This is because if the vector is too distant from the others, it means that it's an outlier. So the weight is going to drop. The same thing, it's going to happen if the match distance is too big. So the patch is not good matched, so we're going to exclude that from it's going to receive a small weight. So the final filter vector is just the average sum of these vectors, of the 3D displacement vectors. So okay, now we have a 3D displacement vector, only one, which corresponds to the translational movement of the person. But we need to move the patches on the image. To do that, we project this filter vector at each height. So the idea here is that it's quite simple, is that we are going to maintain the alignment throughout the sequence, this alignment vertical in the world, but not a vertical line in the image. We are going to see that in the experiments. It's pretty clear. So the last thing I'm going to talk about, or the method, is the scale estimation. It's a very simple technique here. The thing that we're going to do at initialization, we compute the left and right corners of the lower patch, so the patch that is on the ground, and we extract the distance of these corners in the image. So at each frame, we can reconstruct these points in the world using the homography again, and displace them using the filter vector that I show, and project back. Now we have the difference of this distance, and this difference is going to be the scale. So here we only create candidates that are candidates in spatial location, not in scale. So the scale is only that we do. We don't create candidates for scale. Like for instance, frag track use. So now I'm going to show some results, which is better. We use two data sets. The first one is the patch. It's very known, I think. It's 7 FPS. It's in the left. And tau center sequence, which is a full HD sequence. It is in the right. So, and we compare to three methods. The first method, CPD here, is the method that we are based on. So it's the method by Deal. And frag track is it's a non-method. It's also based in fragments, so it also divides the target into several regions. And the last one is TLD tracker, also known as predator tracking, which is a new method. It's tracking by detection. Just to show that. So now, oh sorry, I need to click. So here in the video, we're going to see the patches in green here. It's our method. The others are there. So it was good in occlusions here. And maybe you can see now that the orientation, it's very like that. And it corresponds to the orientation of the person. So this is a good idea also, because as we only assume in the world that the patches are going to be vertical aligned, this could be used at several camera setups. For instance, if you imagine a camera that it's tilt like that, there is a rotation like this, it's still going to work. So the patches are going to be aligned in the person. So now we have a big scale change. You see the TLD tracker here, it changed the person because it's tracked by detection, mainly because of that. Okay, it's a little bit boring. Now we pass the pole. Good. We have a small error there. And this is it. So these are the errors of our method in green. And what I'm going to talk about is that here we are only comparing with CPD, so the method we are based on, and we won with we won in both cases using covariance matrices and also using color histograms. Color histograms are better, but they are more expensive to compute. So we won regarding the old method, and the most interesting thing is that the number of candidates is it's reduced a lot. This is a curve of the number of candidates at each frame. As I said before, it's not constant, the number of candidates in the image. So, for instance, frag track and the CPD track use like 1,000 candidates for each patch in the example that we saw. We are using, I don't know, around 100, a little bit less than that. So it's very good for performance. This is just a comparison to the other methods, the other two methods. I'll show that. And this is the town-centered method. There are more videos in the supplemented material. If you go to the site, you can see that. It's a challenging video because a lot is going to happen here. There's going to be a pigeon that passed by. I think he just passed. And we have partial occlusions. But we have a high frames per second frame rate, and it's full HD, so it's good. Now again, you see the orientation of these patches. So we test for 2 sequences, and the results are better. So now I'm going to show just to show how the performance of the method. I'm going to show some real-time stuff. So I'm just going to initialize 3 targets here, and I'm going to process the whole video. So we see that the frames per second goes around 40, which is quite good because we are using color histograms that are expensive, and we have 3 targets. So, and we didn't do any optimization there. So, just to conclude here, the current work that we are doing right now is an automatic initialization. I'm going to show a brief introduction about that, and the use of detections to recover from failure, because the method doesn't work when you have a complete occlusion for several frames. So the idea that we are trying to do now is to use the person detector to reinitialize the target. So some further work would be nice to have an automatic selection of features. To each patch, we can use different features, which would be, I think, a good idea, and self-calibration, which is for the long run, let's say like that. So just an example here of how we are doing automatic initialization here. So we have the frame. Now we have the personal detector. This detector it's by $1. And we can test each of these detections to see if the height and the aspect ratio corresponds to a person, because we have the camera calibration. So if you have a very small detection here, it's quite possibly false positive. So we do that. We exclude the bad detections using the camera calibration. We use background segmentation to extract the foot and head points automatically, and we create these patches just to show a simple version of the initialization. So this is it. Thank you very much. If you have any questions.
Well, questions?
When you did the comparison, you explored on the other methods the fact that you use calibrated cameras?
A what?
Use a calibrated camera.
A calibrated
You
camera.
explored these characters with
No.
the other methods. So did you think that your good result comes from this fact?
Of course, of course. This is the main idea, is how to use the camera calibration to improve a normal tracker, you see? So the other methods don't use camera calibration. And we are researching for the best way to use this information. But there are not many methods that use this kind of approach, to use this much of the information of camera calibration. I don't know. It's a feature of our method that works well because of the camera calibration. Yeah, it could be, but in our scenario, we don't think that this will restrict too much the approach. Okay. So we are talking exactly on this, like if you have the camera calibration, and in several cases you can extract this information, how you can use that. Okay, so we don't have any methods that try to do in that extent to use the camera calibration. So the comparison, I agree with you, is a little bit unfair, but it's also a feature of the method that works better. Yeah. I disagree. In surveillance systems, I disagree. I think you can. Very strong wind. Come on. No, but I agree with you. It's a limitation. The camera calibration, it's a limitation. But there are some cases that you can extract this information. So a method like this, it's valid in these cases, not in the cases that we cannot extract camera calibration. Yeah.
Actually, at the beginning, I had the same question. This is a good work, but I know the work of Giri Matas, the Kalal 2010, that of course has been designed not for calibrated scenes, because it's working with very general moving cameras, but he had also a version with calibrated camera. So my suggestion was to compare it with other methods. They use the same constraints that you use, just for instance in this case. But I agree with you that there are so many applications where you can suppose to have, or to learn, maybe better to learn the information about calibration. So it's not a limitation, it's just only an initial constraint. But I suggest to compare with the other one. Okay, you're welcome.